So I'll be talking about, okay, Jean-Baptiste warned me that there are not too many stochastic analysts in the group, so I'll try to go slow. Hopefully my assessment what slow means is an accurate one, and give you somehow an connections between the stochastic equations and the deterministic PDEs. Most of you, I presume, are interested in. All right, so what I'm going to talk about is this problem when I'm going to look at the second order differential operator L that has diffusion part that's related to the second derivatives. We'll see why I'm keeping this form sigma x transpose, where sigma is some matrix. It can be invertible, it doesn't have to be. And there is a drift term with the drift vector bi, which is multiplying the gradient in the x direction. If you want to add like zero order term, that's definitely possible. So I don't want to deal with any non-smooth domains. That's like completely open question. We'll see the question as we stated is hard as it is, even on smooth domains. So I'm going to assume that U is a smooth domain, bounded or unbounded. I'm not putting any restriction on boundedness, but many examples are going to be on bounded domains. I'm sorry. The vector and the matrix are going to be C infinity functions. Again, that's for simplicity. There are some improvements that can be made, but for now, let's assume that B and sigma are C infinity functions, and that can be extended on some small neighborhood around U. So there is no problem with irregularity of the domain or the coefficients. What's the last ingredient that is going to be missing? I'm going to look at the ellipticity. So if I take the principal part and multiply it as usual by this psi I, psi j, then I get, this is just the matrix sigma times psi square, which is non-negative, definitely. So it's a non-negative operator, but it doesn't have to be strictly positive. So it's not necessarily an elliptic operator. And our problem is to investigate the linear problem. L of u is equal to some right-hand side f. You can hide your nonlinearity into f if you like. And what's going to be important, I would like to have my boundary conditions to be satisfied in a continuous way. It means that ux is going to convert to gx star as x goes to x star pointwise. All right, again, function f is going to be C infinity on the whole domain, so no problem with the smoothness, and g is going to be continuous on the boundary as usual. All right, so these are my regularity assumptions. Now, what I want to show you why we are actually not solving this one as a direct PD problem, because it turns out to be pretty difficult, but it's actually better to look at this one from the stochastic perspective. So if we have our problem and if we have our operator L, to this operator L is associated stochastic differential equation. And the stochastic differential equation is written in this way. So it's dxt is exactly the drift at the point xt plus diffusion. It means we have our diffusion matrix sigma times the noise. So you can interpret this one if you like, which is formally okay, but non-formally not. I just formally divide by dt, and I get the equation x prime, which is I get the derivative on the left-hand side is equal to b of xt, which is the usual ODE. And then I have something like a sigma xt, and then the derivative of the Brownian motion. Unfortunately, there is no derivative of the Brownian motion, so you need to do something different. But nevertheless, you can view this one as an ODE with the right-hand side b of xt plus some drift, which presumably don't have bounded coefficients if I divide by everything. All right, so this is a r-dimensional Brownian motion. And how this is really interpreted, many people in stochastic analysis are skipping this one immediately. So this is interpreted in the integral sense. So I just integrate this equation and obtain that x at time t is the value at x0 plus the integral of the right-hand side. So that's the integral of bxs ds plus this integral. And now there is a whole theory how to interpret this interval by the Riemann sums, choosing the latent points and so on and so forth. This is interpreted in the ethos sense, and you can see it in some basic stochastic analysis books that this is actually a well-defined integral if sigma is sufficiently smooth. So we are just saying that x of t satisfies this equation. Of course, this is an implicit equation, so there's no like an easy solution for x of t, but nevertheless, it's a reasonable equation to satisfy. And there's a famous Ito formula, which I'm not going to state precisely. I'm just going to say what it is. And it says that if we have a sufficiently smooth function u, then I can actually compose it with my process x of t. And what I get is this equality. So u at x of t in this integral notation is the value of u, of this function u at the origin, plus, and there is going to be this integral term. And what's important why these PD and ODs are connected is that there is exactly this operator L with exactly the same b and exactly the same sigma as above. And this is the integral that we get there as a drift term. Plus, there's something we call martingale, which is, we will see it will drop almost instantly, and it's not going to be important for us. Right, so there's a martingale term. That's something, some probability we are not going to care about, and this is the formula that we are getting if we compose our process with u. Now, the idea is that if u is a solution, if we happen to have a smooth solution of our problem, L of u is minus f, then of course I can replace this L of u by minus f, right? That's a pointwise identity. So I can do that. And this Ito formula actually holds not only for fixed times, but any functions, even that this t can be a random variable. And what I'm going to put here as my random variable, that's going to be the first exit time of my process from the domain. So imagine that I have a domain, and I have some small particle that's moving inside this domain according to this stochastic process, and eventually it will hit the boundary. And when it hits the boundary, I'm going to record, okay, it hit the boundary at the point x of tau. At that moment, I'll stop. And I know that this Ito formula is holding for when I put, instead of t, the stopping time x of tau, this exit time. So this is what we got. And now finally, this is just copying. So we know that u is satisfying the equation and tau is the first exit time. But once we are exiting, we know that we must be at the boundary, right? There's no way that we are anywhere else as on the boundary. But on the boundary, I know what's the value of my function u because it satisfied the boundary condition as well. So on the boundary, we know that this term is actually g of x of t, right? That's what it is on the boundary. That's exactly the exit time from the boundary. And finally, initially, we are assuming that our particle started the journey from the point x0, which is equal to x. So I replace this x0 by x. I replace this u of xt by g of xt, and obtain this formula, which is telling me that our solution at point x must be equal to the expectation of the boundary process. It means the distribution of g when I stop there, when I hit the boundary, plus the expectation of everything that I was visiting during the time of my travel. So the integral between 0 and the time that I exit, and how much I bought from the function f x of t ds. Which really means that, you know, if I have a solution, if I have a smooth solution to this problem, then it must satisfy this stochastic identity. Okay, so that's the main connection. This is going to be actually the formula that we like to be using. Okay. So now there are, of course, many different questions. So first of all, notice that this function u stochastic is defined for any g. It doesn't have to be smooth. It's defined for any f. It doesn't have to be smooth. I never used any ellipticity in the whole process. I never used anything. Right? This is just the universal formula that this actually must be true for any operator L that's of this form. Anything of this form, if I have an associated stochastic differential equation, then the solution must satisfy, if any smooth solution, if there is a smooth solution, then it must satisfy this equality. Now, the question is, of course, is this expression even well defined, right? Are these all quantities finite or not? Does it solve our problem? Okay, so I start assuming that u is a solution of this problem and got this representation, but I don't know if it's a solution. And if it does satisfy, in which sense? Is it a weak solution? Is it a strong solution? What kind of solution is it? Is this solution smooth? Are there any other solutions? Is this the only solution that we are getting, or are there other possibilities for other, say, non-smooth solutions? Okay. But the point is that this solution is defined no matter what are our assumptions on ellipticity, if we have any assumptions on ellipticity or smoothness or not. All right. So let's look at the smoothness of stochastic solution, and we'll see that it's not that easy. So assume that our right-hand side for simplicity is equal to 0. So that really means that this term will drop. This term is not there anymore, the second term. And the first term is just expectation of g of x star. And for the smoothness, say for Lipschitz, I'd like to know that when x and y are close to each other, then the function should be, say, Lipschitz. And if I plug that in, I get that this is the same as expectation when I start with x and hit the boundary, expected value on the boundary, minus when I start from the point y, expected value on the boundary. Now, the usual mumbo jumbo would be you just combine these two expectations and then use some triangle inequality or something. But the point is that g is just continuous. It's not Lipschitz. So there's actually not really a good reason why this should be true unless there's some miracle going on with this x of top. Because if I have a deterministic process, then I have two particles starting nearby. They hit, say, the boundary nearby, but since the function is not Lipschitz, there is no reason why to believe that the solution is going to be Lipschitz. So what needs to happen is that this x star is going to help us, that there is going to be some mixing. It really means that if I start with two initial conditions that are close to each other, they should somehow mix together. And this is just not true for the transport equation. We need the diffusion. So in particular, we cannot be able to decompose our domain into invariant submanifolds that the stochastic process is living in one submanifold. And if it starts on that one and then it's running on a different submanifold, because if they're not mixing, then there's no hope to have any smoothness. So you see, without diffusion, there is no smoothness, and this is kind of a stochastic representation of that one. So, right. Now, the question is this differential equation mixing? Is this SDE mixing or not? Now let's look at this one from like a more naive perspective. So naively, or at least formally, the stochastic differential equation satisfies this ODE. X prime is equal to B of X plus sigma times F prime. And F is some, say, low regularity, not maybe even well-defined, but assume that this is like a well-defined vector. Okay, so this is any vector, R-dimensional vector that's going to multiply our matrix sigma. All right, so the directions that I can actually travel at best is the direction B. That's where the drift is going to point me, and that's where the OD is going to bring me. And then there are directions that are the columns of the matrix sigma. And we'll see why these we can actually travel, that the drift is not going to carry us away. So I can definitely travel the drift when f is equal to 0. And when f is non-zero, then say those are the basic, I'm going to choose my f prime to be exactly the basis vectors of the standard basis. I'm going to recover exactly the columns of sigma, and I can travel in those directions of sigma as well. And there's a very famous theorem from differential geometry by Frobenius that's telling you that foliation, it really means that splitting into these invariant submanifolds is possible if I take the space that's spanned by these x0, x1, it means the drift and the columns of the vector, and I close it under this very weird operation Lie bracket. And if this vector does not span the whole Rn, then we can decompose at least locally into these invariant submanifolds. So that really means that's our enemy. We don't want to do that. So what's the Lie bracket? It's actually construction how you can produce a new directions out of the existing ones. So these are the existing directions that we have. That's the drift plus the diffusion is acting in these directions. Those are the columns of our diffusion matrix. And this is how we can create a new direction. We just travel along the first vector field by the distance epsilon, then the second vector field by the distance epsilon, and then we return we return by the negative time by the direction G1, and then -1 with G2. And the famous identity from differential geometry is going to tell you that we are going to buy a new direction of order epsilon square, which is exactly the Lie bracket of these two vector fields. Okay, so you see, if I do this mumbo jumbo, if I go around this loop, I happen to move in the new direction. That's why this is a new direction that I can create from the existing ones. And this is something that might prevent me to be stuck to the submanifolds. All right, so this is not important, but if you have some vector field, you can write them as like these differential operators, and the Lie bracket is this expression, this neither ugly expression, no matter how you view this one. I'm not going to use this one whatsoever. So if we have some hope for smoothness, then we cannot have we cannot have the process to be splitting the space into the submanifolds. So that really means that by the Frobenius, we need this x0, x1, and xr close under this Lie bracket. They should be spanning the whole tangent space. So there shouldn't be any directions that are not covered either by the vectors or by these mumbo jumbo going around, maybe several times. And that's the famous notion of hypoellipticity. That's the central notion that we'll be using. And again, I don't want to go into technicalities. So again, we have our operator L, which is this one. That's a second order differential equation. And now we are back in PDEs. And we are going to say that this hypoelliptic in some domain V, if we take the column, if they take our vector B, which is a drift term, plus the columns of our matrix sigma. It's important, it's the matrix sigma, not the sigma x transpose, is really the sigma matrix. We close it under the Lie bracket, and we are going to span the whole tangent space at each point of our domain. So if that's possible, that really means that the stochastic process can visit completely the neighborhood. Then there's a very famous theorem by Hermann there, and he got pretty much the Fields Medal for these results. It's telling you that if an operator is hypoelliptic in some ball of twice the radius and these B, sigma, and FRC infinity functions, then if you have a PDE, L of u is equal to -f, then this solution is also C infinity. So that means that if you have enough mixing, if you are able to move in all directions, maybe with the help of this Lie bracket, then you are pretty much recovering the classical theory of elliptic equations. All right, so here is just a very quick remarks about this Hermann theorem. There is a version that's assuming that these coefficients and the right-hand sides are not C infinity, but say in some sublab spaces, and it's telling you in which sublab space it belongs to. This is local results on some balls. Of course, by covering by many balls, you can cover any compact set, even unbounded sets. This is just a local result. You can do whatever you want with this. So you get the interior regularity for any domain, any sufficiently nice domain. There is a version for parabolic equations, of course, because you can interpret time as another space variable. I'm not assuming that this whole problem is elliptic, so I can assume that my time variable is just part of the drift. So there's a little question because T does not satisfy really the same boundary condition as the other ones, but nevertheless, there's a version of this Hermann theorem for that case as well. Just a remark, this hypoellipticity is completely trivial if we have ellipticity, if the columns of sigma span the whole space. Then actually we don't need any Lie brackets. We are spanning the whole space, so we have enough mixing. So everything is trivial. So the classical solvability for elliptic equations just follow from this Hermann theorem. And here is like very quick remark. Imagine that I have a second order operator, but which is degenerate when x is equal to 0, because in that case the second derivative with respect to y is equal to 0. But then I have two vector fields. One vector field is just 1 and 0, which is corresponding to derivative with respect to x. So this is the x component, there is nothing in y. And the second one is degenerate, which is 0 and x. that's coming, remember, x is coming from the sigma, which is kind of the square root of the coefficient. But if I take the Lie bracket of sigma partial x and x times partial y, that I have this new direction y that I was missing before at 0. So this operator is hypoelliptic. So the whole theory, whole solvability holds for these operators as well. All right, so this was solved, you see, like 55 years ago. It was completely solved, the questions about interior regularity. But for the bounded domain, the question is very tricky, and surprisingly, it's not resolved in a sufficient way. So, okay, let's go back to elliptic operators because we are very familiar with those. So assume that we have a Laplace, which is a nice elliptic operator, as nice as you can. And the question is it possible to find a harmonic function which has a zero boundary condition? Harmonic function which has a prescribed boundary conditions on the boundary of a domain D, and it attains the boundary condition in a continuous sense. So this was conjecture of Riemann from 1851. You see, I cannot write just 51 because it's actually 1851, not even 1951. So it's a very odd conjecture of Riemann if this problem is always solvable, because he had already this variational characterization and he thought that this is going to be always true. However, in 1912, Lebesgue provided a counterexample, and but the statement, okay, so the domain was very rough, right? That was the point, and I'll get to that one, how rough it needs to be. And he actually showed that the statement is true, that this problem is solvable if all the points on the boundary are regular. I'm not telling you what the regular one is, but sufficiently nice. And in another 12 years, Wiener provided the necessary and sufficient condition for the regularity of a point. And it's based on the capacity of the set. You probably read this one in this basic PD book in the Evans or in the Gilbert-Rüdinger and so on and so forth. They have these like whole theory of capacity. And then there are like whole theory of non-smooth domains, how we are going to interpret the boundary condition and so on and so forth. Very difficult theory. It's not completely clear what's the geometric meaning of this Wiener condition and so on and so forth. The intuition pretty much is that every point on the boundary is going to be regular if you can comfortably access it from outside of the domain. And what comfortable means, I'm not going to define right now. So, for example, the counterexamples are you take a disk and remove the origin, and of course, you cannot access it from the outside of the domain, so you shouldn't really prescribe the boundary condition at the origin. Or you just you take the disk and then remove the radius, and again, you shouldn't be imposing any boundary condition on this segment, because this is not like a true boundary. All right, so our goal actually is to understand how the regularity of boundary points for the equations that are not even elliptic, so they are just hypoelliptic. Why do we need this one? Because if we know how to understand the boundary regularity, then we can prove the well-posedness on bounded domains for hypoelliptic problems and other results. Because so far, if we don't know in which sense the boundary conditions are attained, then we have no uniqueness, we have no even existence of solutions. So we need to understand boundary regularity. Interior is understood by Hermann there, boundary is not. And we'll see that it's different. So let's look again at the stochastic representation, and this is going to be a big help to us. And remember that our stochastic equation has this form. And here is going to be a very soft assumption. So I'm going to assume that our process is going to exit the boundary, the domain with probability 1 in finite time. So this is a usual assumption. You need just a little bit of diffusion, especially for bounded domains, for this one to be satisfied. If you don't have any boundary to exit, say you are working on RM, you need some assumptions on the boundedness or compactness on G and Fs for these processes to be well defined. I don't want to go into that one. This is assumption that you can satisfy with not even that technical assumptions, but we are assuming that actually, especially the Sto is finite with probability 1. And what turns out to be true, which already was known to Wiener, is the question of regularity of the boundary points. It doesn't really matter if it's elliptic or hypoelliptic or anything like that. The boundary is regular, if and only if this state Immediately. So if it has this chaotic Brownian motion, we know that that's true, but it's not clear how that happens for the general stochastic differential equations. So here the exit time is, of course, the first time where we are not in the closure of the domain D. So that really means that we exit instantaneously. Now, there's a beautiful probabilistic result by Kolmogorov. It's telling you that if we are working with events that are infinitesimally small, then they have probability either 0 or 1. So we either exit instantaneously with probability 1, or we exit with probability 0.
So, sorry, can I interrupt for a second?
Yes, please.
So, so your current definition of regular points involves this kind of stochastic process, but so you let it run in the whole space, right?
So yeah, I'm not talking about the whole space. I'm talking only about the boundary points.
No, right. So you pick a point on the boundary, so your x0, and then you run the stochastic process starting from that.
Yes.
But you actually allow the thing to get out of. So in some sense, the stochastic process is allowed to get out of your domain, right?
Right.
The domain for that, you need the velocity field. But for that, the B vector field should be defined also outside of omega, so that your problem makes sense, right?
That's right.
In terms of PDEs, that's completely weird, right?
Right. That was my original assumptions that that this matrix B and sigma are defined on the neighborhood of U bar.
Ah, okay, I see.
So
okay,
I can I want to have the situation as simple as possible. Otherwise, you use
right. No, I see. Okay. But so really, the values of B really matters inside of omega, and since they're smooth enough, you kind of extend them, because otherwise, in terms of PDEs, it's weird that you define the notion of. I see. Thank you. Sorry.
Yes. Right. All right. So if we have an elliptic process, then we know that this guy, it has all the directions, so it's completely going to explore the small neighborhood for any small time. So the point is that it's going to explore the whole small ball. And that really means that if we want to have a point which is not regular, then the outside of the domain should be very, very small, negligible, right? It's like you cannot access it comfortably from outside. And this is kind of the idea of this Wiener criterion. If the boundary point is not accessible from outside, that really means that our process, even elliptic, cannot really exit D, then this problem is not going to be regular. Bad luck. All right, so what can we say? What are the irregular points for the hypoelliptic diffusions? So again, the regular point is we need to exit with probability 1 immediately. So first of all, it might be tempting to say that hypoellipticity is going to take care of that one as ellipticity did, but actually it's not true. So imagine that I have this stochastic differential equation that's working in 2D, and in the y direction is pretty much the Brownian motion, so it's jumping back and forth as it likes. But in x direction is just yt squared times dt. Pretty much that xt prime is equal to yt squared. All right, so xt prime is yt squared, so it's always positive, the function is always increasing. So the process can never exit through the y-axis, right? So if you are living in the right half plane, then x is increasing and it will never exit. That's the bad luck. So the boundary condition on the y-axis are never going to be attained in a continuous way. You can prescribe whatever you like. You're never going to see it because the process is not going to ever access this y-axis. So the points on the y-axis are not regular, and you can easily check that this problem is still hypoelliptic. So it's moving in the x direction because we have a right drift in that direction. And then it's moving in the y direction because we have a diffusion there. So it is a hypoelliptic operator, not a problem. And there is a more interesting example, if you like. There's a 3D case. Again, in z direction, we are moving as a Brownian motion. Y is pretty much y prime is z, and x prime is y times z. So, okay, y prime is z. X, I just integrate, is integral between, is the integral of y as ds. I plug it in for z. I get this y as y prime s, and if I integrate this one, I get yt squared 1/2 of this one, which is again always positive. So this process, although hypoelliptic, is never going to exit through the x equal to 0. So it's never going to reach x negative. And it didn't start there. So there are irregular points for these diffusions, even though we are looking at the completely smooth domains with a flat boundary. It cannot be smoother than a segment in 2D. All right, so there's a PD criterion that's going back to also the school of Wiener that's based on the barrier functions. And this, again, like somehow recollect what we said about the PDEs. So it says that if we have an x on the boundary and it has an open neighborhood and a function which is positive on this neighborhood and 0 at that point, and at the same time this W is a subsolution for hypoelliptic L, then elliptic or hypoelliptic, then the point is regular. So this is like a PID criterion. I'm not going to use it, it's just recalling. Now, but you see, a construction of these functions W is pretty problematic. It's not easy to do. So there's some work that's done in this direction from the PD in the PD setting by the Italian mathematician Cogloi, but it's definitely not optimal because it's not completely clear what they're going to do for the in the hypoelliptic setting. So here's the first result that's saying something about the irregular points, and it says that irregular points are pretty rare in a way if you're willing to modify the boundary. So if you are in a reasonable domain, it means that domain U is C1, it's convex and bounded, and there's a technical assumption you are not containing any part of the hyperplane. It really means that it's never flat, completely flat. Here's the main assumption that you have a vector, fixed vector V, that belongs to the column space of sigma. So I have a fixed direction for every x in which the diffusion is acting. Then I can actually find the domain, which is a polyhedron, which is inside of U, that has the piecewise linear boundary. It means it's a polyhedron. All the points on the boundary are regular and is as close as U as you like. It really means that the measure between U and this V epsilon is less than epsilon. Right, so why this result has any meaning? Because if we are working on the domains and we are working with some numerical software, say finite element methods, we need to approximate the domains by polyhedrons anyway. So kind of a random polyhedron is going to give us reasonable numerical simulations and the regularity. So, but this is not the main result I wanted to discuss. All right, so let's go back to the boundary regularity and let's look at the results for the Dirichlet problem. So imagine again, I have a Dirichlet hypoelliptic problem, L of U is equal to 0, and I'd like to know that U is equal to G continuously attaining on the boundary. And recall that we have this stochastic representation, that U stochastic is equal to expectation of G of xt. And I have the standing assumption that I'm exiting the domain with probability 1 at finite time. That's the standing assumption. Okay, suppose that D is a bounded smooth domain, L is hypoelliptic, G is continuous, our usual assumptions. And if we are assuming that all points on the boundary are regular, that really means that if we start at that domain that we instantaneously exit, then this stochastic representation is the unique bounded classical solution of our problem. So this is indeed a solution. It's smooth. It satisfies the equation in a classical sense, and it attains the right boundary conditions, and it's the unique solution of the problem. So here are some remarks. As I promised, I'm not going to do too many proofs today, just overview of the theory. So interior regularity requires a little bit weaker assumptions. We don't need to be bounded, all the boundary points to be regular, only accessible points to be regular, but we don't know which points are accessible or not. So let's assume anyway that all of them are regular. And we have also the local version of the statement. It really means that if X is regular, then this point, solely this point, is continuously attained. So it's a regular statement. It's a statement about how the boundary conditions are attained for if only some points are regular. There are extensions to unbounded domains. We can do that with some natural assumptions about, the finiteness of this expectation and so on and so forth. And we have actually two proofs of this one. One is to regularize a stochastic process to make it elliptic, which really means to add like epsilon times Laplace to our hypoelliptic operator, which makes it elliptic. And the regular problem, we have no problem with solvability on smooth domains. But then we have to still compare the trajectories of our stochastic equation and the regularized stochastic equation. And this is definitely not a trivial task, because these guys are visiting everything. These guys might be almost deterministic. So it can go that they just go to the boundary, hit it, turn around and leave, and not exiting the domain. Whereas these guys will exit the domain. So there are some things that that needs to be done, because these two processes are very different. There's actually alternative approach, which is even better than this regularizing approach. It's giving better results, cleaner results, and more general results, that we actually work directly with the density of the stop process x of t until it reaches the boundary. Again, I don't want to go into details here. So, all right, so we have also results for the Poisson problem, and then you can combine those two. For the Poisson problem, again, we are assuming that we have the right-hand side, which is C infinity, and now the boundary conditions are 0. If you want to combine these two results, if you have the combined problem. And again, the stochastic representation is now this integral of f of xt. So just a warning, even if f is just 1, it's a super smooth, nice constant function, then here we have an integral of 1 between 0 and tau. And in order to be able to speak about any finiteness, that we need the right-hand side to be finite. So that really means that the expectation of the exit time should be finite, which is a little bit stronger than expectation that the probability that the exit time is finite, that this is 1. Right? Please, question.
Yes. So you say that here in the idea of the proof, I was wondering if a similar proof, but along the more standard lines of PDE would work. Like instead of solving this equation, you solve the equation where you add to the left-hand side plus epsilon times the Laplacian of u.
Right. So people tried that one. Everything works fine up till you reach the boundary points. In the boundary points, there is actually not completely clear what are you going to do from the PDE point of view. If you have these barrier functions and that question of regularity, then yes, you can do that. But other than that, it's a very fine analysis around the boundary. How and which processes are going to exit the boundary.
Okay. Okay.
So that's actually the problem from the PDE standpoint. It's like people tried and it doesn't seem to be that easy.
Okay, thank you.
All right, so we need this assumption, and we are actually going to, the expectation of tau should be finite, and we are actually going to assume a little bit more. We are going to assume that if I go look at this tau y, and y is living on some small neighborhood of point x, then this whole thing is uniformly integrable. It's not only pointwise integrable, it's not the expectation is finite for every y, but it's somehow uniform. Okay, so it's a little bit technical assumption to allow us to passage to some limit. And again, the statement is if all the points are regular on the boundary, then this is the unique smooth solution of our Poisson problem. Right? Right. So we have also the local statement. It really means that if just one point is regular, that point is going to be attained continuously by this formula. Regular proof, you can regularize, and again, it's pretty much the same approach. The whole problem is how to compare the trajectories of the hypoelliptic problem, which might be deterministic, and stochastic one, which is jumping all around. There's an alternative approach that investigates the density of the stop process as before, and there is a use of the Green's function. So even the Green's functions for the hypoelliptic problems, and I think this is like a cleaner and more straightforward way. This is the way how it's supposed to be done. All right. So we have consequences. So we have well-posedness for this hypoelliptic problem, and there are many consequences that we actually included with David Herzog in the paper. So we have estimates and analysis of the Green's functions for the hypoelliptic operator. So what I mean by that one, that's another nice probabilistic formula. Imagine that I'm looking for the problem. I regularize it a little bit. So I have L minus beta times U is equal to F. But eventually you can put beta is equal to 0, even beta to be positive. And let's look at this probability. So P of X is going to be probability. P of S is a measure on sets. And the measure is like this. I'm looking at the probability that I start at the point X, I run my process, and I'm asking what's the probability that I exit my domain exactly through the set A. Okay. So I can be exiting on anywhere on the boundary, and this is kind of measuring what's the probability that I exit exactly through A. All right, so this is the distribution of the boundary of the stop process. Now it's actually, I'm going to use the formula. So if I use this formula again, now with the easy modification for beta, so that I don't have to worry about integrability. So I have an integral between 0 and tau f of x s e to minus beta t, beta s. Since I don't want to deal with this tau in the boundary integral, so I just multiply it by the characteristic function of my set. That really means that if I exit, this is going to be 0. And then the expectation is the same as the integral against this measure. That's pretty much probability 1. That the expectation is the integral against the distribution. So I just integrate it against this distribution, interchange the integrals, and I realize that my formula, the solution, is actually integral over d of a function f of y times this function, which is probability that I exit through this infinitesimal set dy, and this is the integral between 0 with respect to time. And this is something that we call the Green's function. Okay, I'm not going to use this one, but you see there's also like a good probabilistic interpretation for the Green's functions for these stochastic equations. Okay, so we are able to, with these techniques, we are able to analyze the Green's functions and get estimates for that one. We get also a slightly new proof of this, slightly improved proof of this bonus Harnack inequality, which is kind of a Harnack inequality for the hypoelliptic equations. Those are the PDE results. We are also able to say something about the stochastic processes. We are able to get the criteria for the recurrence, transience, positive recurrence of the process, existence and uniqueness of invariant measures, and so on and so forth. So there are pretty good consequences of these results. All right. So let's go to the boundary regularity again, because I was a little bit cheating, right? These results are like really mathematics results. Suppose all the points on the boundary are regular, and the regularity is really meaning that we exit at time 0 instantaneously. Now, the question is how to verify the point is regular. So we need to analyze our stochastic processes for very, very short times. We are asking, are we going to exit immediately or not? So that should be some asymptotics at 0. All right, so let's see first the intuition. So let's say that I'm looking at the Brownian motion. So that really means I'm going to look at the solution of the easiest stochastic equation. Just d of x is equal to dw, x is just the Brownian motion. So again, another famous result in probability is the law of iterated logarithm, which is telling you the wt divided by this horrid expression of the double logarithm is actually equal to 1. So it's telling you that by time t, Brownian motion pretty much covers this interval, pretty much square root of t plus times some correction. The Brownian motion gets pretty much square root of 2 distance from the original point. There's a more precise version, which is more useful for us. That's called the Strassen's law of the iterated logarithm. And now I'm not going to look only at where I'm going to be at time t, but I'm going to look what kind of function I'm going to follow by the time t. So that really means I'm going to look at the function. This is a function of time. Now I'm going to send epsilon to 0. So that really means that I'm looking at the whole function on the interval, say 0 and epsilon. T is between 0 and 1. And I just rescale it. And it turns out, and there's a very nice connection to the whole Sobolev spaces, it's telling you that this Brownian motion, if I watch the Brownian motion, rescale it exactly by this Brownian scaling, in the limit, I get any function in W12 in the Sobolev space. Bang, surprisingly, what the Sobolev spaces are doing here, right? Brownian motion is not anyhow in the Sobolev space, by the way. And those are the functions that have the Sobolev norm less or equal than 1. So the Brownian motion is going to visit pretty much any Sobolev function in the unit ball. Okay, so that's the result for the basic probability. Now, this is the intuition. So the Brownian motion is going to visit everything, is going to visit the points at the distance roughly square root of t times something else, right? Now the drift, the constant drift, which for CNT functions is assumed locally, it's going to be constant. It's going to travel the distance roughly t, right? So the drift is going to carry you at time t roughly to the distance t. The Brownian motion is going to drag you to the distance square root of t. Now, square root of t is much, much bigger than t. So that really means that the Brownian motion, it really means the diffusion is the winner for short times, and it's going to kill the drift. So that really means if we have a Brownian motion in each component, that really means elliptic, then the Brownian motion is going to completely ignore the drift. I don't really care what are the drift terms. So it's going to cover every single direction. And that's the result why the ellipticity is actually, why the lower the terms do not matter if they're smooth enough. So for the elliptic equation, it doesn't really matter because the diffusion is just way stronger than the drift. It's going to win. All right. So let's do this a little bit more precisely. So I'm going to look at my stochastic equation, starting at the point x. I'm assume for simplicity, but it can be done in full generality that the matrix is constant. I'm going to rescale the time. So I'm going to shift to x, rescale the time by this Brownian scaling, and shift it back to x. Then it's easy to see that this y, it's really super easy to, it's going to satisfy this equality. And now we see, look, this guy, this fraction is going to 0 because I have square root of epsilon that's going to 0. And here is the log of epsilon, which is, okay, we're still going to 0, but unfortunately this square root of epsilon is much stronger. So this term is going to be killed. But this one, look, I have the Brownian motion divided by the right scaling. And by this Strassen's law of iterated logarithm, I know that I'm going to, in the limit, get any W12 function with norm less than 1. So eventually, as epsilon goes to 0, this term will disappear. And I'm going to follow any path that's described by the Sobolev 1 norm function. So same reasoning, if the matrix is onto, I'm going to visit every single direction. So the points are going to be regular. All right, let me steal 1 more minute. So if we try to do it for the hypoelliptic equations, then here are the results that I'd like to show you. So if we try to do it for the hypoelliptic ones, then we are going to associate for our equation a new equation, which is kind of a rescaled equation. And we are going to assume this our main assumption that our coefficients, as the rescaling goes to 0, are going to converge to some b and sigma, not necessarily the same as the original ones. That's definitely not the same. So this is going to converge to b. This is going to converge to some sigma. And we are hoping that this Brownian motion is going to converge to some W12 function. That's what we are getting in the limit. So we are now going to look at our limit equation, which is now a well-defined ODE, because this is derivative of the W12 function, which is an L2 function. We have a good theory for that. And the B and sigmas are smooth. So we have this sigma, we have this limit equation, and we can analyze this one. And there are some issues about the blow-up. We don't know if it's well-posed, blah, blah, blah. If it's a well-posed in W12, we are able to solve all these issues. And here is the result. So suppose that we have the convergence, and then for almost surely we have these conclusions. So for every solution, we are going to associate so-called Kramer transformation. That really means I take the solution and I'm going to take the smallest right-hand side that's going to give me this solution. Okay, so that's the solution that's going to give me exactly this G. Possibly there are several of such Fs, and I'm going to take the minimal norm, the H1 norm of that one, all right? And I'm going to look at all the points that have this Kramer transformation less than 1. So again, if it's a Brownian motion, we are looking only at the H1 norm less than 1, which is going to recover our Strassen's law of iterated logarithm. And now the whole main theorem, I didn't put this out, again, our result with David Herzog, it's telling us that these trajectories for sufficiently small epsilon are relatively compact, and they are going to converge exactly to the set x k of x under the scaling. So, and this is the second statement is a little bit more complicated, but it pretty much says that every point is attained with probability 1. So this is indeed the limit set of every single trajectory of our differential equation. Okay, and this is true also for small epsilons. All right, do I have like 2 more minutes for an example?
Yes, you have 5 minutes.
Okay. So let me just show you how to apply the whole mumbo jumbo. So I have 2 examples. This is easier. This is, I think this is better. So imagine that I have this equation. And so d of x1 is x1 squared minus x2 squared dt. d of x2 is 2 times 1 x2 dt plus the noise. Now, you see there's some question about there's x1 square, x2 square. Maybe it's going to stay only on one side of the domain. Maybe there's some blow up, right? There is a d of x1 is x1 square. There is a risk for the blow up. So this is possibly explosive. But, okay, so we are interested in the short time. Are we going to visit the whole neighborhood or not? Is any of those guys, this is a positive one, this is a negative one, is any of those going to win? Are they equal? What's happening? All right, so what we are going to do, we are going to rescale. So the first component we are going to divide by, second component we are going to divide by r of epsilon, which is this is exactly what we need for the Brownian scaling. By the way, r of epsilon is in the first example is exactly the Brownian scaling. So I'm going to divide by that one to get it over here. Recall our main result requires here to exactly have the Brownian scaling on the bottom. So that's what I'll do. I divide by that, divide by that. But in order to do this one, let's look. Here is the scaling that I'm introducing in the second variable is r epsilon. What's the scaling of the first? You see, it's going to be r epsilon square because this component enters as a square, but there's also the time derivative, which is going to, by the rescaling time, is going to introduce one more epsilon. So if you think about this one, this is actually the right scaling that you do. And if you rescale it, it's an easy task. There's almost nothing to do. You just divide by these factors. Then you get this system of rescaled equations. And now you see, if epsilon goes to 0, this is the classical Brownian motion. So it will converge to any W12 function with norm less than 1. This guy is going to 0 because epsilon square is just stronger than the Brownian scaling. So this one will drop. This one will stay. That's how we actually rescale the whole thing. And this term will drop. This is negligible. So in the limit, our limit equation, when it passes epsilon to 0, we have this easy system of ODEs. And I can solve that y2 is pretty much f of t, and y1 is the integral between 0 and t f of s squared ds. So for short times, the main theorem is telling us, for short times, the profiles are exactly these functions. That's the limit set, are exactly the solutions of this equation, where f of t is less or equal than 1. So you see, in particular, this integral is bounded. There's no blow up. And then we are getting pretty much any value, any reasonable value m, but it's always negative. So our process, if I rescale it back, say the first component with this scaling, which is epsilon r square epsilon, in the limit is going to have the value minus m, the lim inf, and lim sup is going to be 0. So that really means that it's not going to exit certain domains where you need to move in the direction of x1. So you can actually say which domains is this guy going to exit, in which this is not going to exit. All right, I'm pretty sure that I'm over time, so proof is based on large deviation principles, pretty much by the spirit of Friedland, Wenzel, or Kashminsky. And there are still many open questions about accessibility of irregular points, criteria for regularity, without actually solving the ODs, but saying to immediately getting it from the coefficients and so on and so forth. Okay, thank you for your attention.